All right, so today we're gonna finish off definitely the first refinements, and then I would like to start just a little bit about the second refinement, just to see what the abstract state is, talk about its abstraction, maybe some basic stuff, and then we'll do the more, like a deeper stuff, maybe week, okay? So your lab number 4 has been released. Take a look at that. And there's a reference paper I pointed out to you. You can take a look at the E-class. You will see the paper there as well. It's going to be very, informative paper, really, just to see the context for using tabular method. And course evaluation, right now it's about 40%. So guys, do your best. Again, it's optional. Don't feel really pressed to really do it. If you want to do it, you can still do it before 10 p.m. We'll see how close we are. If you're fairly close, I really don't mind, extending the early participation window to be maybe even over the weekend. But let's see how close we are. Okay. Any questions about the course? Yeah.
Regarding the information sheet that we are allowed to bring for the exam, is that the A4 size, double size?
It should be letter size, right? I think in North America, usually it's the letter size, right?
Letter size, single side?
Single-sided.
Okay.
Mm-hmm.
All right.
I'll try to give you guys maybe the exam guide. It's usually a PDF. It's really the same information as last year. I'll try to see if I can make it available before Tuesday, so you can take a look first. Yeah. Again, for the data sheets, you don't really have to work alone for yourself. I don't mind if you guys kind of collaborate, share some parts. It's definitely okay, right? Just make sure you bring the sheets you really feel the most comfortable with to the exam. Okay. I'll give you guys more information. Okay, a little bit later. All right, let's now do a recap, okay? All right, and then we'll move on. So last time we actually talked about the difference between invariance and also variance. Invariance, in means not. Variant means to change. No change means stay the same, always, right? If you try to kind of analyze what that really means literally. So invariant is really just a Boolean expression that should always hold to be true. That's something we'd like to, something that we want to stay as a system property. So especially for safety property, for example, you want to make sure the breach is actually one way, right? You only have either A is 0 or C equal to 0, things like that. Okay, invariance. And for variance, it's actually an integer expression. Again, this variant here is not really the solution for deadlock, not the solution for lifelock. It's really a way to really measure how many times you're really interleaving the new events. And then if you're trying to interleave the new events way too many times, potentially infinitely many times, in that case, there's an alarm for your system, right? So you may have to do something about it, right? So please take a look about these two, right? And then we simply just try to trace about, for example, like this particular trace, you can take a look. We're going to look at a similar trace today once we get to the second refinement. We're just going to see how the system state is going to change. Okay? And then when we plot everything about the variant value here, we got this diagram here. Very quickly. In general, you want to remember for the O events, in this case, either ML out or ML in. They can either increase the variant value strictly, or they can keep the value the same, either way. Or, and then if you got new events, IL in, IL out, it's going to strictly decrease the variant value. So you got two conditions here to be maintained for the variant, and they are stated as proof obligation. Number one, the variant value should always be a natural number, larger than or equal to 0. This one here usually will be quite easy to prove. It should not be difficult. You just have to choose the right hypotheses, maybe using monotonicity. It should be quite straightforward. This one here could be a little bit trickier, because somehow you want to show that whenever you got any new event happening, right? If you think about it's doing a transition, the post-state value over here should be a lower value. The pre-state value here should be a higher value. So you're really strictly decreasing the value. Right? So that's something you want to remember. So we want to make sure when you try to decrease the value, you're not really decreasing to the extent that it's going to let the variant value go below 0. That way, it's an alarm for the system. Okay. And then it's an exercise for you guys to give a try. For example, if you try out any other variants, are you able to see the pattern as well? Okay, that's really the exercise here. Okay. So in the exam, you want to be able to, for example, number one, if I give you a particular trace over here, are you able to show me the trace and then to show how the variable value is going to change. That should be a very simple exercise. You just have to be patient and also careful. And can you actually plot the variant value accordingly as well? You just got to evaluate it and then plot it accordingly. And another thing you want to be able to do is to make sure once you got a variant value, are you able to show that the variant may be appropriate? To really show it formally, you have to, number one, to formulate all the proof obligation using these two, right? And then formulate a sequence and show that if they are provable. If, for example, in this case, we got 2 new events and 2 proof obligation for each, we got 4 of them in total. Formulate all 4 of them and try to prove them. If you cannot prove any one of them, then there's something wrong with your model about life lock. Okay. And then we also spoke about some new inference rule. So these rules will be useful for today after we talk about relative deadlock freedom. That's something we're going to start with. That one's going to be tricky, so that's why I want to get it out of the way in the beginning. Okay. And right here. All right, guys, any questions? All right, awesome. Okay, let's start with the tricky part right now. All right. Okay, relative deadlock freedom. Okay, let's take a look at one thing here. Okay, so the slides you want to look at will be here, slide number 81. Okay, so this part here, just about guard strengthening, deadlock freedom. You know, these are the relevant stuff that we kind of talk about before. So you can revisit when you actually study for the exam about this part. So what we need to talk about now is something called relative deadlock freedom. Not exactly just deadlock freedom, but relative deadlock freedom. Okay. Let's talk about it right now. To start with, whenever you talk about relative deadlock freedom, it must be in the context of a refinement model. If you're only in M0, we don't really talk about relative. There's nothing relative to it. So it's really about the refinement model. Okay. So relative deadlock freedom is really something you have to, should be proved for a refinement model. Okay, just clarify, especially the word relative, meaning that we're comparing abstract and also concrete. All right. So now let's remind ourselves very quickly something. Okay, if you recall guard strengthening, let's write it down just side by side. Guard strengthening. Okay. Does anyone remember? Should it be concrete implies abstract, or abstract implies concrete? Concrete implies abstract. Very good. Okay, let's get it straight first. And then you'll realize in the deadlock freedom is completely the opposite. Okay, so that means concrete, which would be HI, some concrete guard, implies the abstract. Okay, of course, there was a whole discussion about guard strengthening. Okay, so that's something you can definitely review. So I just wouldn't actually add any distraction to it, just about talking about it. But you can definitely look at that from the previous lecture material. So this one here is a concrete guard. The concrete guard of some events. And this part here is the abstract guard for that particular events. So this is the abstract guard of that events. Okay, so this is just a reference point, so please review it once we talk about relative deadlock freedom to really compare them. All right, so now let's look at the relative deadlock freedom. Let's start with just the proof obligation itself, and then we'll go from there to see some intuition. As one of the hypotheses right here, this is the disjunction of all the abstract guard. And if you also recall, okay, maybe it's worth to really go back to a little bit earlier in the lecture. Okay, I want to show you that right away. Okay, so just bear with me. So there is one page that when I first talk about deadlock freedom that I refer to, right here. Okay, so please revisit this page over here. Okay, we talk about, let's say for our M0, if we actually got this particular condition here, where we got the disjunction between the guard of both events. In this case, we only got 2 events. So this disjunction here consists of the disjunction for all the events. So this is saying either the guard of this is true, or the guard of this is true. Or in other words, either this is enabled or this is enabled. So we call this the deadlock freedom condition. So this is the condition where the system is guaranteed not to really deadlock. It's really away from the deadlock. On the other hand, if you actually got this condition completely the opposite, that means event number 1 is disabled. Event number 2 is disabled. Every event is disabled. In that way, it's going to be deadlock condition. Yeah?
Because I know that like this is only deadlock freedom conditions are only for reactive systems. How are we supposed to tell when and when not to use like deadlock freedom? Or maybe I'm not making the question right, but when, like, what systems will we only be given reactive systems?
It's a good question. Yes. So one thing is deadlock. Well, deadlock itself is kind of neutral term. It really depends on the nature of your system. Let's say, for example, if your system is just supposed to be go from one state to another and terminates, in that way, deadlock is not a bad thing because eventually it has to terminate. So, but in our case, the bridge controller is a reactive system, so we say deadlock is bad. So in the exam, if you're given a system to prove about deadlock freedom, in which case you just get a formula accordingly. If you somehow have to judge whether deadlock is really a good thing or bad thing, you will be given explicit hints about whether we are talking about reactive system or not. If that's a reactive system, deadlock should be bad thing, right? Yes, yeah. Good, it's a good question. Good. All right, guys, so my point is, so please make sure you understand about deadlock condition versus deadlock freedom condition, okay? That's something I want to draw a connection to right away. And let's now go back to where we were. To this page right here, okay? So this one here is saying the disjunction of all the abstract guard, okay? Let's put it down first and then write down the interpretation. So this is the disjunction of all abstract guards. In other words, so this is a deadlock freedom condition for the abstract model, all right? Another way to put it is, so this is the deadlock freedom condition. So deadlock freedom condition for example, M0, in our case, abstract, right, M0. On the other hand, if you look at the goal right here, so this is, again, this disjunction, but it is the disjunction for all the concrete guards. Okay, let's also put it down. So this is the disjunction of all concrete guards. Okay, and then, so let's also put down as the interpretation. So this will be the deadlock freedom condition for the refinement model, or concrete model, in this case, M1. So there's a deadlock freedom condition for M1. Okay, let's get it very clear first. So we are saying if the abstract system does not deadlock, that implies the concrete system should not deadlock. That's what it really says logically. But we're going to visualize that a little bit just to see, exactly what that really means. Okay, before that, let's now try to have some principle done. Okay. As your fellow student pointed out, so it's very important to clarify the context, like a development context over here. We talk about reactive system. Okay, so principles. Okay. So, number 1, for our context for bridge controller, deadlock is bad. Deadlock is bad for reactive system. Reactive system is supposed to be reactive all the time. It should not deadlock ever. Okay? So now, consequently, whenever you're trying to introduce a refinement, the refinement should not introduce any new scenario for deadlock. All right, I'll write it down first. A refinements should not introduce a deadlock scenario not existing in the abstract model. Okay? If the deadlock situation is already known in the abstract world, it's okay to still keep yourself to be still deadlocked. But however, if in the abstract world, that one is not a deadlock scenario, in the concrete, it cannot be a deadlock scenario. All right? Anyway, I'll do a little bit more visual. Okay? Let's go step by step. So here, a refinement model. In this case, we're talking about M1. Right? That's our refinement model. And we also talk about abstract model, which is our M0. Okay? I got two visuals over here. This is the legitimate scenario where the relative deadlock freedom is the case. This is the illegal situation where relative deadlock freedom is not the case. We'll talk about both of them just to get an idea, just to be complete about why this one is good, but this one here is bad. Okay, we're going to see exactly. Question first. Yeah.
Yes, in the GAR strengthening, we already know that the edge, like the new GAR for the old event, need to be stronger than the edge of the concrete event. Sorry, of the concrete model should be stronger than the GAR in the abstract event, right? So at that time, when we draw the Venn diagram, the G is bigger than the edge, right? And here you draw it in the opposite way. So is that the reason because of a new event?
Not really. New event can definitely be something. Yes, you can say that, yes. So however, I would say maybe the best way to really think about these two, like a GAR strengthening and also relative deadlock freedom, is to think about it independently. Because as you said, they're kind of in the opposite direction, right? And also what you mentioned about new event is definitely another dimension as well to consider. I'll try to see if I can compare them maybe a little bit more. But today, let's focus just on the relative deadlock freedom to begin with. Okay.
All right.
Yeah. Question? Oh, you're great, right? Okay. I thought you said question. Yeah. Okay, good. Okay, let's talk about it. Okay. All right, so given these two principles, what is unacceptable? All right. What's really unacceptable is the concrete model should not introduce a new deadlock scenario. It is, you know what? I will try to make this part here a little bit smaller. Just this part. Oh, sorry. Just this part. Okay, anyway, let me just write it down. It is unacceptable and let me see if I can have any space over here. Okay, let me write it down here. Sorry, just need to find the proper space. Okay, put a star here. Okay, I'll put it here. It is unacceptable if there is a states where the abstract model does not deadlock. But the concrete model does. Meaning that we should not introduce any new scenario in the concrete model that deadlock. Okay, but we'll see visually. Okay, but let's write this down first. Unacceptable if there's a state where, okay. Let's look at this one here, all right? So here we just say G and H, they're somehow not related to each other logically, right? Just two different sets over here, okay? For this one here, you can see this right here, just look at this part here. So if you look at just this part, just this part, okay, just this part here. So what does this part really mean? Let's see. Okay, you can see this part here is where the G, which is the abstract guard, actually holds, which means the abstract model does not deadlock. Let's start with that first, okay? Just this part here. So this one here is where the abstract model is deadlock free, because their disjunction of the guard is simply true. However, this area is exactly outside of the disjunction of all the concrete guards. What does that mean? That means this area means the concrete guard is simply all false, in which case the concrete model actually deadlock. All right? Also need to write it down. And also this part here is really where we have not the case. We got H1. I'll just say H1 all the way to Hn. I'm going to omit about constant and also concrete variable, just to be short. Okay? H1 all the way to Hn. All right? And this part here simply means the concrete model is not deadlock free. That would deadlock. All right? This is the part where the concrete model is not deadlock free. If this particular area is not empty, then your refinement model is not considered as valid, because you're creating some new deadlock scenario. All right, I'll write it down. Okay, so if you can find any states inside, for example, right here, okay, so this is a state where, number one, the abstract model does not deadlock. The abstract model does not deadlock. But the concrete model deadlock. Right? So these two are together. Right? Are we okay with this diagram notation here, just to see where we are? Okay? So this is a scenario where we see that the model is not good, because we're introducing a new deadlock scenario. Okay? What should be good? This is exactly what the G implies H is really specifying. G implies H. So what does that mean? Okay, let's just look at this one here. Okay? This one here is saying, for all the scenarios where the abstract model is deadlock free, you want to make sure the concrete model preserves them, no less. All the deadlock free scenario of M0, the abstract, are preserved. Because whatever that's in the abstract, not deadlock, is also in the concrete, not deadlock, right? So that's number one. Number two, it is okay that we also got this area not empty. What does that mean? There might be certain scenarios where the abstract model deadlock. However, in the concrete model, it's not deadlock anymore, which is okay, because we're talking about reactive system. It's okay for you to unlock certain scenario, not to be deadlock anymore. Okay. Might sound a little bit tricky, so that's why I want to mention everything at one go, and you can take a look, maybe when you study for that. Okay, so this one here simply means it is okay to have scenarios where, okay, I'm running out of space, I'll put it here, where the abstract model deadlock, but not the concrete model. Because if you think about it, This is the area where we got concrete model, not deadlock, right? That's a condition. At the same time, this is already outside of this area. So you can think about right here. At the same time, this is not the case G1 or GN. Okay. Okay. Any questions about this one in general? Okay. I'll try to maybe compare again, possibly Tuesday or next Thursday, to see how we can kind of compare scar strengthening also relative to deadlock freedom. But for today, let's focus on this one only, just for you to get used to it first. Yeah, question.
I found this question very similar to the question you have in the task 2. The stronger, weaker, but however in here, apparently the abstract deadlock freedom is apparently stronger than the one in the concrete, right? So how will you explain that, like why? If, for example, if you introduce it does not introduce any new event. The refine does not introduce.
No, intuitively thinking this way, right? Simple. For all the scenarios where the abstract model does not deadlock, you want to make sure all those scenarios remain deadlock free in the concrete.
So that was a design requirement.
That's a requirement, yes, because we talk about reactive system. Deadlock is a bad thing. Anything that used to be not bad, it cannot suddenly become bad in a concrete model, right? So you want to make sure all the scenarios that do not deadlock in the abstract, you want to make sure when you go to the concrete model scenario, those scenarios still remain to be deadlock free. On the other hand, it is okay to say in the abstract model, I used to have certain scenarios that used to deadlock. But now suddenly in the concrete model, I unlock those scenarios by allowing some progress to be made.
So we could have it, but not necessary.
Yes, we could have, exactly, right? Because this diagram here, when you think about implication, it could be that this disjunction here, you can think about this disjunction here, and this junction here might be completely equivalent because implication can be can be bidirectional. Not necessary, but could be the case, right? In that case, the abstract and concrete will be just the same circle. In that case, the deadlock scenario for the two worlds are completely the same. It's also possible, but we're just saying cannot be. So I think that this might be the most important sentence. We want to make sure all the deadlock-free scenario in the abstract is preserved, no less.
So that's the responsibility of designer.
Designer, yes, exactly.
Okay,
yeah, exactly right. Yes. All right, guys. Yeah, question.
So going back to that, if we look at the guard strengthening, which is
Yeah.
HI proves GI, which automatically assumes that HI is a refinement of GI, but it's within the constraint of GI. So in this case, if we're not considering new events, why would the deadlock freedom of HI, the concrete values, be weaker than the abstract?
Right. So that's something I'll try to maybe compare a little bit more next time. Yes, I definitely see that. But as your fellow student also pointed out, when we talk about the abstract guard, of course, these are only the O events over here. But here we actually talk about you can see also you can see the index over here. You can see we got M here, we got N here. That means potentially the number of disjunct we are putting together might be different between the two disjunction, right? So this will be the disjunction for all the abstract events, O events basically. And this part here might be in addition some new event as well. So those new events might just allow more scenarios, right? That may not be deadlock, right? Yeah, good. All right. So guys, think about this one here. We can definitely revisit. I'll try to give you a little bit more summary, maybe Tuesday or Thursday, just about this compared with this. Just think about this a little bit first, as a first exposure. Okay. Having known this, let's now do the easy part, because I think conceptually to really understand what this really is more important. But once we understand it, let's now try to see how we can prove it, right? So we can go to proof obligation, okay? So now we just state the proof obligation quickly, okay? We got axiom, abstract invariant, concrete invariance. Let's get them first, okay? So we got these three over here, okay? So I'm going to write it down. So axiom will be D, N. Oh, by the way, in the exam, right? You don't really have to put, for example, M0 and 1, like what they really look like. In case I really want you to formulate some proof obligation from some model, I'll give you the model, right? So you don't really need to put these information in the data sheets, right? Just in case you're wondering, right? Okay. So D larger than 0. Okay, and then we got abstract invariance, which will be n, a natural number, and also n less than or equal to D. All right, we got concrete invariance, which will be A, B, and C, natural number. C, natural number. And also we got A plus B plus C equals N, the linking invariance, and also A equals 0 or C equals 0, the safety invariance. Okay, very quickly. These two are the axiom. These two are the abstract invariance. And all these are the concrete invariance. Okay? And then, what about this part? Right? It's going to be the disjunction of all the abstract guard, which is going to be this one here, this one here. Okay? So we got n less than D, n larger than 0, right? So you can think about this part here. Oh, maybe I should have used box to confuse you. So how about this? Just for this part here, it is the deadlock freedom condition for the abstract model. Deadlock freedom of M0, all right? And after this, we should really have the turnstile, right? So that one there is going to be the disjunction of all the guards, right? Including also the new events, as you guys correctly pointed out. That's very important, okay? So we actually got, let me highlight them. 1, 2, 3, and 4, all right? 4 of them. So we got A plus B less than D, and C equals 0, right? So that's this one here. Or, let me put them down, and then I'll put disjunction. Also, C larger than 0. Also, A larger than 0, right? C larger than 0, A larger than 0, and also these two, right? And also B larger than 0, and A equals 0, right? You can see each new line for the guard is like a conjunction, as we said earlier. We're going to put them together by disjunction, okay? So it's going to be disjunction, or, and or. And this part here is about a deadlock freedom condition for the concrete model. So deadlock freedom. I can write better. Of M1. All right. All right, so that's a proof obligation, which is not difficult to really specify, okay? And good thing is you don't really have to worry about post-states version of the constraint, which is good. We don't have to worry about before-after predicate. It's about guards. All right, that's an exercise for you to see how you can prove this one here, all right? I would say definitely give a try on this. If you haven't seen the proof yet, it's a very good exercise to see how you can prove it, right? You can think about this more like a hinted version. I kind of told you about what inference rule you can actually use, right? You can definitely take a look, right? Or you can start from scratch to see how you can prove it, okay? So you can split that into two parts. Think about, you start from here, you're gonna have some inference rule apply, and then this will be some intermediate step. That'll be the beginning of part 2. Once you get there, and then you can eventually get to some proved sequence. So it's quite a long proof, okay? And you can definitely find the solution on the slides. But if you look at the lectures page, I can also show you there's also one nice presentation of the proof. So if you look at under sequence proof, so first refinements, right here, possibly here, okay? Yeah, relative deadlock freedom, right? So that's a proof. Well, once you print it out, you will see, okay? Kind of a nice way to organize it. Yeah, question?
Why can't we use the C equals 0 or C greater than 0 just to fully arithmetically prove?
Sorry, which step are you talking about?
Not any step in particular, just looking at the sequence. And in the conclusion, there's C equals 0 and or C is greater than 0.
Are you referring to the slides or the page? Which one are you referring to? The slide, okay? if you're referring to the slides, and then you can just tell me which slide you're talking about. Not this one here. Is it here?
Yeah, so on the sequence, the first one.
Oh, the first one.
Yeah. Does that and change the fact that can we not use the C equals 0 and then C is greater than 0 like, separately? Or is the and like kind of lock it into that?
I see what you mean. It's because to start with, we have to make sure we kind of follow the proof obligation itself, right? For example, let's say here. So we are really talking about, let's say for here. This one here is because we actually got one guard and two guards. And then they are actually separated by a new line. So that means we're going to put a conjunction between them. That's why we got this one here. And then that one there alone, we put a parenthesis so that we know that it should be one unit to be disjoint with the rest. Yeah. Mm-hmm. Yeah, I think that this should be the first look of the sequence to really show that you really try to combine all the four guards together using disjunction. Once you got to that step, you can definitely do all sorts of simplification as you wish. Yeah. Okay. All right. Okay, so let's now just take a 1 minute or two just to, so we are now done with the first refinements. Let's just summarize about what we have achieved for the first refinement quickly, and then we'll take a short break. Okay. So for the first refinement, right, we basically got this initial model, which we showed to be provably correct, and that's what we have been doing in the past few lectures, right, just about the first refinement here. So you can see we got A, B, C, and then over here we got all the invariants, all the guard, etc. So every time you actually got refinements, as we, after the short break, we're going to talk about second refinements. We have to worry about also the same set of proof obligation, right? So we talk about, for example, guard strengthening. Let's just see the first one. When I talk about guard strengthening here, I got to make sure the concrete, for example, the concrete must imply the abstract, right? So that's just one example, okay? And also we talk about invariant establishment. That one's for sure, in which case we got to look at the inits, okay? And also we talk about invariant preservation. Invariant preservation should be just for all the events, including the old and also the new, right? You can think about all the events should be subject to invariant preservation, all of them, right? And the new stuff that we talk about in the refinement is about convergence or lifelock, okay? Convergence or lifelock, okay? We'll use these two terms interchangeably, okay? So these two. And convergence or lifelock. To really measure that, to see if there's any presence of lifelock, potentially, you have to specify something called a variance, an integer expression. And then we have to make sure we prove two things about the variance, right? Let's do some quick reminders. We got two associated proof obligation. We had to prove about the variant value strictly decreasing by all the new events. And also, we got to make sure it always remain to be natural number. Natural number. Okay, like that. And then we also talk about relative delta freedom just today. Okay, that one there is about disjoining all the abstract guard together. Should imply the disjunction of all the concrete guards right here. Right? That's something we just spoke about today. Okay? And when we get to the second refinement after the break, we have to, first of all, talk about all the variables we need to worry about, and also all the events, some new event as well. And then we have to revisit all these 1, 2, 3, 4, 5 different proof obligation. Right? That will be for next week. But today we'll do something maybe a little bit lighter. Questions? Okay, why don't we take a break? Okay, and we'll take attendance as well. All right, so we are now done with the first refinements. The slide has been updated. I think this will be the final version of the slide. So if you really want to print it out for your exam study, you can feel free to do that. I don't think there will be any major changes. I don't think so. It's pretty much stable. So if you actually go, okay, let's see. So that's the final delta freedom proof. You can definitely give it a try yourself. Okay, first refinement summary, which we just spoke about as well. All right, so now we talk about second refinements, right? So second refinement, not too, there are only a small number of topics that we have to go over, but they're rather tricky, especially the final one or two. So we're going to be more careful, okay? So, but we still got 3 classes. I think we're good in terms of covering all of them thoroughly, okay? So today, very light, I just want to introduce about what the second refinement is going to be about in general, intuitively, and also introduce some variables, some invariants. If time permits, we can also talk about some events, okay? And then we'll dive deeper next Tuesday, okay? All right, second refinement, basically we want to zoom in even closer to see the island, bridge, and mainland, the whole thing, right? So now we're going to see more variables to be introduced, okay? And then we're going to see that. Okay, let's now see it, okay? In this particular second refinement, that will be the last refinement we do. For just, this is not required by the course, but if you're really, really interested in seeing how this bridge controller can really go into, I think in the textbook, the Event B book, they got one more refinement, like a third refinement to introduce, like a sensors, actuators, which we don't really cover. So, of course, since we don't cover that in the lecture, they will not be covering the exam. Only for those of you who might be interested. Otherwise, we can focus on just the second refinement. That'll be enough. Okay. So the second refinement is going to handle 3 more E descriptions, okay? Environmental assumptions. Let's take a look at them. So E description number 1. The system is equipped with 2 traffic lights, each one of them green and red. Just 2 colors, not 3, okay? Just for simplicity, red or green, okay? So we actually got 2 traffic lights. 2 traffic lights. Each one of them will be green and red. And we'll see exactly these 2 variables and also associated events in the actual model, okay? And we got another 2 description over here. So these are also important assumption, right? So these are not something that we're going to encode in the model itself. It's simply something we assume, okay? So let's read it together. The traffic light control the entrance to the bridge at both ends. So there'll be 1 traffic light right here for car to really go from mainland to the bridge. There's another traffic light right here for car to really go from island to the bridge. So these are the 2 traffic lights, right? So the physical locations for the lights, okay? Another one here, okay. The cars are not supposed to pass on the red traffic lights, only on the green one. It's a very fundamental assumption. Otherwise, whatever property we prove about a system doesn't make sense, right? We've got to make sure driver really obey the rule. If no, the model is going to be much more complicated, okay? Good. So that's something we want to clarify first. And then we'll do a little bit of overview, okay? So these 2 are the fundamental assumption. Without these assumptions, it'll be very hard to predict the model behavior. Because you don't even know when the light is actually red, can there be any clash, right? You gotta make that assumption, very important, okay? Let's now put all the 3 models together, right? Remember the very first initial model, where we kind of collapse the island and the bridge into 1 compound, right? That's M0. And in the past 1 or 2 weeks, we actually talk about M1, where we got one-way bridge and also island split. And we got the 2 new events right here, right? And also we got A, B, and C. Oh, question?
Is the bridge still one way?
It's still one way, yes, definitely. We just add something on top. Yeah, you will see, yeah. So M2, exactly right here, is still a one-way bridge. And in this case, I'll explain that in a moment. We still got A, B, and C accessible to us, okay? And we got 2 traffic lights. So the main additions are the 2 traffic lights. So here we got mainland traffic lights, island traffic lights. Okay, so these are the 2. And there will be 2 colors, for example, green and red, green and red. All right, so these are the simple model. And if you're ever interested in going to the third refinements, I think there will be some sensors on the different locations, but it's outside the scope for this course. Okay. Let's now just go over some basic concept, right? And then just some overview, okay? First of all, let's talk about the visibility of the variables. When we actually try to specify our M1 right here, we said that N here is not exactly accessible by the events. For example, you never saw ML out, IL in, they modify maybe the N variable, right? You never do that. We simply just say maybe just modify A, B, or C, right? However, now we're going to see another kind of pattern which will be allowed in refinements. Somehow we are trying to kind of accumulate A, B, and C into the concrete model here. Okay, I'll write it down. So let's now just revisit what we knew before. So here we only, in the abstract model M0, we actually got just the variable N, the number of cars in the compound, just N, right? So when we actually go from M0 to M1, all right? So we go from M0 to N1. The abstract variable N is not accessible by N1, especially the events, event guards and actions. All right, that's what we knew earlier. But we're going to relax that restriction, which is possible, right? Of course, whenever you want to create a refinement, you can kind of choose which flavor you want to go for, all right? So when we go from M1 to M2, right here. So we go from M1 to M2, right here. M1 to M2. M1 to M2. Okay? The abstract variable in this, okay, if you only look at these two, this is abstract, this is concrete. However, now if you look at M1 and M2, this is abstract, this is concrete. Right? As we said earlier, they're relative, right? So when you go from M1 to M2, the abstract variable, which is A, B, and C. A, B, and C. These are the abstract variables. A, B, and C. They are accessible by the concrete model M2. M2. Okay? So this particular pattern here, where the abstract model somehow got its variable inherited to the concrete model, is called superposition. Okay? You will see that term also on the slides. Okay? Just a special term. It's called superposition. Right here. Okay? And if you want some analogy, right? For those of you who still remember some details in Java, you know, when you actually put variable visibility like a modifier, right? So you can think about over here, the N here is a little bit like a private, which means it's only visible to the abstract model. On the other hand, the A, B, and C, they are somehow like protected. So they can be inherited to the concrete model, right? Just analogy. If you're okay with it, you can go with that intuition. Okay. Think about the A, B, and C here are more like a protected. Yeah, if you forgot about exactly the private protected visibility, don't worry about it. It's not that important. Okay. Okay. So what we have is you can see A, B, and C. So these are from. Okay. So these are from N1. Okay. MLTL and also ILTL. Oh, let's just explain the words over here. So this means mainland traffic lights. Okay, mainland traffic lights. Okay, so this one here is island traffic lights. Island traffic lights. So these two are the new variables in M2. All right? Okay, all good. And in this M2 here, which we'll see in the coming 2 or 3 lectures, we're going to talk about the correctness of this second refinement. What should we cover in the correctness? Okay, let's write it down. The correctness of refinements. All right. Do you guys remember what kind of proof obligation should we address? We don't introduce any new proof obligation though. What we learned about in M1 is already that'll be it. We're going to repeat them again for M2. Graph strengthening, that's good. I agree. Okay, what else? Relative data freedom, okay, sure. Relative dialog freedom. Life lock, yeah, life lock, like life lock divergence, right? Yeah. So basically about, life lock. Yeah, I'll get there. Life lock or divergence. So Diego, did you say something? Okay, yeah. What else? Yeah, right. Don't forget about that, right? Because invariant, we still want to do that, right? Okay, so number 4, you want to make sure the invariance is actually both established and preserved. All right. These are all the things we're going to cover again, right? Just to see how we can apply them to more variables, which means the proof will be a little bit more sophisticated. Okay. All right. I would suggest we just do very quickly some invariants, not too many, just to see how we can specify them. Should not be very difficult, and then that'll be it for today. I don't need to go too deep. We can save the deeper one once we start fresh on Tuesday. I think guys can focus more. If you want to do a little bit of study over the weekend to start preparing for the exam, you can look at relative dialog freedom. I think that one's a little bit tricky. Okay, just 1 page, and then we're good. So let's look at the model for M2. Right, just remember you got 3 E descriptions to really cover for this model. And we got A, B, and C from M1. We got the new variables MLTL, ILTL. So these are 5 variables we have to be concerned about for this new refinements M2. Okay, so the static part, we actually introduce a new carrier set color. Okay, red or green for traffic lights. Okay. And then axiom here, we say color is exactly green and red. Okay? And then we say green is not equal to red. It's like a numeration type in Java or in programming language. We want to say they are not the same constant. Okay? Okay, pretty simple constant. The axiom part. And for variables, just reminder, you can just remind yourself, A, B, C, they come from M1. And ILTL, MLTL, the 2 traffic lights, they are the new variables for M2. But of course, they are all accessible for us to use. Okay? And we got invariants. The first 2 are just typing variants. We're just saying what's the type of the traffic lights. And of course, you're saying MLTL, ILTL right here. So it's going to be either red or it could be green, right? Either way. Very simple. Okay, why don't we just practice about specifying these 2 invariants, and then we're done, just for today. Okay, yeah, question.
For the static part of the model, if we put it in the broader environment, does that mean the context?
Sorry, say that again.
So for the static part.
Oh, you want to put in rodent?
Yeah, put in rodent.
That's correct.
Is the context? Right?
That's correct. That's correct.
Then shouldn't all 3 model M0, M1, M2 using the same context?
You can say yes. They do share some common part for the static part, like a D, for example, the capital D, I remember. So the capital D is still here. I just didn't put it here. But I think you may have to just introduce some extended context for M2 because you only have the idea about traffic light, like red or green, in the M2.
So when you do refinement of the model, you also adding you might also want to add some new content in the context.
Absolutely. Remember, the very idea about refinement is to introduce more details into your model. what can the additional details come from? It could be some additional detail for the context, and definitely some additional detail for the variables in the dynamic part.
All right.
Yeah. Good. Good. Yes, please.
Why do we need to specify axiom 2,2 if we are explicitly enumerating the set color, and if it's a query set, it's supposed to have distinct elements though?
It's a good question. So the fact that we say that these are the two members of the set, right? I think it's this inequality here, in some way, is not strictly necessary. It's actually useful. It's more like a shortcut for us to like a lemma. Later, when we actually want to prove certain property later, if you can use this axiom directly, so you don't really have to use to say, oh, these are the two members, so they should be different. Right? You can use this one directly. It's like an additional property you can use.
Okay, but it shouldn't be, I mean,
It's not strictly necessary, let's put it that way.
So technically, you could use arithmetic to say that because color is constituted by green and red, they cannot be the same.
Yes, you can say that in some way. Yeah. Question?
For invariant 2 and 3,
Mhm.
this is just my thought. Would it be like ML_TL equals green implies?
Oh, you mean this one? Oh, we'll get there. Yeah, you're adding, yeah, I know you want to go home, but not yet. Okay? Almost. Yeah, of course. Well, we're going home very soon. Okay, very soon. All right? Let's now do some quick exercise, but you're actually quite right. Okay. So let's talk about invariant. Okay, so here you can see that the 2 here is about M2, right? Just remember the naming convention, right? This is M2. And we got 4 invariants in total, 1, 2, 3, 4. And notice that in this case, we don't have any linking variants. We don't have to link between the abstract and concrete because in some way, they are not really related. It's like additional variables. So you don't really try to relate A, B, C together with MLTL. Not quite. You might specify some logical connection, but not like a linking variant we saw earlier. Okay? So we wouldn't call these two linking variants. Okay? All right, let's now talk about these two. Okay, the first one. Being allowed to exit from the mainland. If some car is allowed to exit from the mainland, okay, given that that's the antecedents, that would mean the cars currently is being limited. So we're still under the cap, basically. And then there's no crash possible, informally. All right? We can break it down. So here, of course, when I say means, it's really a way to really say implies, right? Okay. Okay, implies. Antecedents over here, for example, we say being allowed to exit the mainland versus being allowed to exit the island. So really talking about if you're able to exit from the mainland, going this way, or when you are going this way. We'll talk about it independently first, right, in the invariants. What does it really mean when you're able to go from here? Like what you said, that means the car will going to follow the traffic light. That means this one should be green, for example, right? Okay. So that one there, I'm going to put it down. So that means the MLTL equals green. Should imply something. Versus over here, ILTL equals green. Should imply something else. All right? So these are the two antecedents. Yeah, question?
Maybe the ML_TL equals green implies that ILTL is red, so that like there's no crash. Would that be it or no?
It's good. It's interesting. Yes. You're basically saying when this is actually green, then this one must be red. Okay? That's something we would like to show later. However, I think at this point, you want to go a little bit deeper into it. You may want to refer something to do with the A, B, and C. Okay? Because just to say this is actually red may not be sufficient. Okay. Okay, I'll go with you first.
I was thinking A plus B is less than B, and C is equal to 0.
Yeah, obviously, if you want to go for this way, you want to make sure there's nothing going this way. That means C should be equal to 0. And symmetrically, if you want to go in this way here, you want to make sure A is also 0, right? Let's make sure that part is actually done. Okay. So no crash and no crash. One will be the C equals 0. The other one is A equal to 0. Okay. C equals 0 and also A equals 0. Right? Just about this part. What about limited cards? That means over here, the A plus B here, it should still be strictly under the cap, right? That one is not bad. That one there, right here. Limited cards. And A plus B strictly less than D. Okay, cannot be equal to, because that's equal to right now, adding one card is going to go right above the maximum. All right. All right, finally, there should be at least some card in the island. We have done something like that, right? You got to make sure that there's at least one card here so that one card can actually go this way, right? So B larger than 0. Okay, very easy invariant to actually get right. Okay. Any questions about this? Okay, so I'll need to stop here today, but I would say before next Tuesday, you can definitely take a look at the states, ABC, MLTL, ILTL, and look at the relative Taylor freedom and the stuff. You can start definitely going over the material for the exam. I'll try to give you guys maybe the exam guide, especially the guide that's about data sheets sooner rather than later. All right, thank you so much. I'll see you next week.